Okay, so let's begin. We'll wait for a couple of more minutes to see if anyone joins. Then we can start. We'll be starting by 5:05. Okay, so let's begin. So welcome everyone. This is NOC EE-91 NPTEL tutorial session on semiconductor devices and circuits. The course instructor is Professor Sanjeev Sambandan from IISc Bangalore. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar here. So every week we go live from 5 to 7. So some prerequisites, as I reiterate every time, that it is expected that you have gone through the previous week lectures posted on the course web page, and also it is expected that you have attempted the assignments posted at least once by yourself, so that you can be able to grasp the concepts carefully. Okay. So Okay, welcome again. It is week 9. So we'll begin with today we'll be discussing the MOS capacitors. Okay, today MOS capacitors we will discuss. So what is special about these MOS capacitors? So let's understand that first. So MOS capacitors are basically nothing but your this kind of structure. Okay, there will be some metal. This will be, it will be like this. It will be some metal, some insulator. This is generally silicon N or P type. This is generally your silicon dioxide. So that's why the name came that it is metal oxide semiconductor. Okay. So basically this kind of structures are also known as MIS structures. Okay, which is more general name. This is same metal insulator and it is as usual semiconductor. So let us take some cases. So far we have discussed your metal semiconductor junction. We have discussed PN junction. We have discussed high-low junctions. And we have also discussed your PIN diodes, right? How the band diagrams, how the charges are there, everything we have discussed. So based upon our knowledge on that and some additional information, some additional physics you should know, that from that you can analyze this kind of structure. Okay, to analyze. So again, what kind of junctions are here we are forming? One junction we will find at this place, right? This junction, and another junction we will find at this place. So this junction is what? Your metal insulator junction or interface. And this is your insulator semiconductor interface, right? What we are interested in to see that if you apply some potential, let's say this terminal you take grounded, you can do other way around also. You can apply potential here also and make this one grounded. So effectively stating that with respect to other terminal, if you apply some voltage here, how the characteristics of this device changes, right? So as you can see, firstly that this region is your insulator region, right? So there will be no current flowing. Current flowing would be zero because you have a insulator. The insulator, we will assume that it is ideal insulator, so it does not conduct. Okay. So now I want to ask you certain cases. So you see that it is neither falling in this metal semiconductor junction part, neither it is falling in PN junction, neither in high-low, neither in PIN. But yes, PIN, some part, insulator and semiconductor, this part or this part, depending upon what type of substrate you are using. This is called your substrate you are using. You have this kind of this knowledge we will be using. Okay. So first let me ask you some basic steps. So what happens? Suppose this is a metallic block. Okay, this is a metallic block, metal. What happens if I apply some potential here? What do you think? What will happen? Let's say this is ideal metal. and this is some source. Let's say it is practical source, not ideal. That cannot be present. Okay, so can you please unmute and tell me what will happen?
Current will flow through the metal.
Just wait a second. Yeah, can you please speak now?
Current will flow through metal.
Wait a second. You are less audible. Current will flow, right?
Yes, sir.
Okay, so how much current will flow?
Uh, V is equal to IR.
V is
Potential
equal to
divided by resistance.
IR. So your I is equal to V by R for an
Yes, sir.
ideal metal. For an ideal metal, what is the definition of an ideal metal? Sigma is infinity, right? That means
Yes,
your
sir.
rho is 0. That means your R is 0.
R. Yes,
That means infinite amount of current will be flowing, right? Or basically it
yes,
will be very large. And why very large? Because you see, you have always a source resistance in series with the battery also, right? So there in this entire loop, there will be this RS will be present, but this RS is generally very small. So what happens? It is like you have a battery and you are just shorting this battery, right? So have you ever seen by shorting the two terminals of the battery what happens? Yeah,
short circuit.
no, short circuit is a different thing. Have you just have you just shorted the two ends of the battery? Generally, this starts to heat up and this starts the wire melts, right?
Yes, sir.
Even if your wire can because the wire will also have some resistance and it will create your I square R resistance heat, right?
Yes,
This
sir.
I square R heat will be, as your current is very high, this heat will be increasing the temperature and eventually your it will cross the melting point of the wire and it will just the circuit will then get open circuited and it will be lost, right? So this is what there will be. So ideally, what you are telling that it is nothing but just an extension of the wire. And why do we do that? Because there will be no potential drop, no potential drop across the metal, right? Just an extension of your wire or your ideal wire. Okay, so that is fine. Now tell me, uh, what happens if this block is an insulator?
It act as an open circuit.
So no current will flow, right? I equal to 0.
Yes, sir.
It
I
will
is equal
be
to 0.
insulator. So it will act as like this, right? It will act as an open circuit. So if it acts as an open circuit, the entire voltage Vs will be appearing here, right? Across the two terminals of the insulator. The entire voltage will be appearing there because there is no current in this paths or through these leads. Okay. Okay. So now tell me what happens if I do this. I have a, let us go with the 2D drawings. I have a metal and then I have an insulator. This is metal, this is insulator. What happens now? Yeah.
Vs come across the insulator.
VH will come across the insulator, right?
Yes, sir.
Because again my metal is nothing but it will act like a short circuit and VH will come across the insulator. Okay. Now remember this point. Okay. So potential will drop across insulator. Entire potential. Okay. Because no current is flowing. So now tell me, we have studied this also, right? This PN junction, PIN diode. We have studied this PIN diodes, right? So how did we go about it? Firstly, as it is N side, so around this region there will be some acceptor ions and there will be some dopant ion, right? Under full depletion approximation or depletion approximation, you will have something like this kind of charge profile. Okay. So how will my electric field profile will look like? So how will E look like? What is your E? E is nothing but E is what?
Electric field.
No, right. But in terms of rho, it is like this, right? What is this law?
Poisson's law.
No. This is called Gauss law, right?
Yes, sir. Differential form is Poisson's law.
No. Same thing. Poisson is nothing but your del square phi over del x square equals to minus rho by epsilon. Okay. Another higher order derivative. Okay. This is your Poisson equation. This is your Gauss law. Remember that. This is nothing but the same thing what you study in your electromagnetic field theory. Right?
Yes, sir.
This is your Gauss law. Same thing is this. And why do I write that? You know about this operator, right? This is a three-dimensional derivative, or it is called.
Del operator.
So this is your rho. So this will be nothing but epsilon times rho, epsilon times E, electric field. So this is constant, rho by epsilon, or in 1D, what is this? This will be like this. This and these are same, right? So this is Gauss law. Remember that. So under Gauss law, what we can see that this step function will behave like a ramp function, and then this 0 will have a constant value, and again it will fall and the electric field will be like this. Do you agree with that?
Yes, sir.
This we have discussed, right? Last week.
Yes. Yes, sir.
And at this junction you have a Emax. So similarly, what will be your potential profile? Again, potential profile will be nothing but it will be
Again,
some
again
reference.
differentiation.
No.
Yes, sir.
How come potential be differentiation? It is minus integration of Ex dx, right?
Sorry, sir. Integration. Yes, sir.
So it will be your this thing will be quadratic, then it will be linear, then it will be again quadratic and then straight, right? This kind of behavior you will see. Fine. Now notice one thing very carefully, that what happens at the, and what is this I, by the way? I is nothing but your intrinsic, right? Intrinsic type. That means the entire stuff is, what is the base, by the way? The entire base, or what is the base material? It will be silicon, right? Here it will be, let's say it will be arsenic doped, it will be boron doped, and here it will be no doped. But the base material or the host material will be silicon itself, right? Now let us take another case. Let us take some SiO2 and silicon surface, okay? And let us apply some potential. This is your insulator. This is your semiconductor. Okay? And let's say it is, what kind of doping you want to take? Let's say it is p-type doped. Okay? So how will the charge profile look like? Can you comment?
Till origin it will be
In
0,
SiO2,
and then
let's say this is your
step
SiO2 and this is your silicon N-type, p-type. So how will the charge profile look like in SiO2 region? What is the free
SiO2
charge?
0,
SiO2 is an insulator,
no
so there
free
will be
charge.
no charge, right? And what will
Yes,
be in
sir.
the p side?
Step function,
Step function. Why?
because it is p-type, acceptor ion will be there.
So there will be certain amount of acceptor ions, right?
Yes, sir.
So now if you draw the, from rho to, what do we go next? Rho to electric field.
Yes, sir.
So now can you comment on the electric field? How will the electric field look like? This 0 will be some constant
Yes, sir. And
and this
step
will
will
be,
be ramp function. Integration of step will be
the
ramp
ramp will
function.
be with a negative slope, right?
Yes, sir, with the negative slope.
So you mean to say it will be like this, right?
Yes, sir.
But this is wrong. Why do I say that? That is the additional thing which you require to, this additional part I have mentioned, right? This additional concept you need to know. So what happens is that, so far we have discussed with the same base material. That means on silicon we will be using various doping, right? You see, the base material is silicon itself. That means the entire stuff is of silicon with different kind of doping. What does that mean? That your epsilon r is your always 11.7, right? That tells you about the material property. But what happens now? What is the epsilon r for silicon? Epsilon r for silicon is around your 3.9, right? And epsilon r of this is 11.7. So earlier what do we have? We had this condition satisfied because there has to be continuity in the electric field because it is in the same material. Okay. Now what happens is that, suppose you have a two materials. Okay. Now remember your electromagnetism, EMFT course, electromagnetic field theory course. There you have seen that if there is two material, ER1 and ER2, let's say, and it is subjected to some field lines. Okay, let's say some field lines are there, not in this direction. This direction is also fine, but for the better understanding, let's say this direction, some electric, it is subjected to some electric field. Okay, or some field for that say. So at the interface, what happens is that there will be a component at this side. Let's call this EN1, and there also will be a field component at this side, at the right hand side. So let's call it EN2, the normal component. The horizontal component or along the surface will get cancelled out, okay? But what happens is that this EN1 and EN2 are related in, these are related, okay? And how they are related? The displacement vector has to be continuous across any interface of two various kind of materials, okay? Let me write it down. Displacement vector is, what is the displacement vector? This D, right? Displacement vector is continuous across interfaces if there is no charge per se. So what will happen? So your dn1 will be equal to dn2. What is your dn1? dn1 is your epsilon 1 times e1 en1, and it will be epsilon 2 times en2. So if we remove the epsilon zeros, then it will be simply your epsilon r1 times en1 will be epsilon r2 times en2, okay? So if your epsilon r1 is equal to epsilon r2, that means you're at the boundary, the continuity of the normal component of the electric field will be maintained. Otherwise what will happen? ER1 is not equal to ER2, so your EN2 will be, let's say, ER1 over ER2 times EN2, right? This equation will hold. So now you see it is 3.9 and it is 11.7, right? Almost 3 times. So your, let's say this is, we will define it that E ox and we will define it at ES, okay? So let's say your, at this boundary, your E ox time epsilon ox will be equal to ES time epsilon S. So E ox, you know this line because it will be some constant, right? Constant line. So now what will be your ES at the boundary? Can you tell me what will be ES? ES will be nothing but E ox over ES times the electric field at that place. So what is this quantity? This will be nothing but ER ox times E0 over ER S over E0 times E ox. This will get cancelled and this is your 3.7 and this is your 3.9, it is 11.7, right? So 1 over 3 of E ox. That means at the silicon side you will have a jump here and then it will fall like straight line, okay? Because it will get integrated, this part will get integrated, but there will be this distinct jump. And why does this jump is happening or discontinuity in electric field? This is due to the fact that my silicon dioxide and silicon do not have same relative permittivity or dielectric constant, okay? So do you get the point?
Yes, sir.
So now if I ask you that how the potential profile will be, so how the potential profile will be, so this will get integrated.
Yes, sir.
Phi is nothing but what? Minus of integration of ex dx.
Yes, sir.
So this fellow will be straight line,
Yes, sir.
fine, and your this straight line will be, this will be your quadratic, and this will be your linear, right? And notice the fact that the potential remains continuous, right?
Yes, sir.
But again, it is not differentiable at this juncture. Why? Because the slope of this line, because this line is not matching with the slope of this curve at this point, okay? This slope is this one, and its slope is at this point is this value. So there is a distinct jump, and that is due to we are dealing with two different kind of materials, okay? So keeping this in mind, everything else is will be based upon whatever we have discussed in this part, because now we know about how my metal insulator works and how my insulator semiconductor works. Now just I need to join these two, this one and this one, where this part will be common, okay? So let us do that. So this much part you please remember. Okay, just let me, I do not know. Okay, so let's begin then solving the problems. So what is given here is that, given a band diagram of p-type semiconductor, a band gap this, okay, this is p-type. By the way, can you tell from the band diagram itself that it is p-type if it was not written? And how would you tell that?
EF is near to the EV.
Or more profoundly, you can say that EF is below EI, okay?
Yes, sir.
Suppose I am giving you this kind of band diagram. Suppose uh, this is your EF and this is your EC, this is your EV. So you may not know whether it is drawn to scale or not to scale, okay? So always ask for what is my EI. If it is below EI, then it is EF, then it is P type, okay? It need not be very close to my EV. So it is a comparative distance between EC and between EV to EF, okay? So always try to tell in that sense that it is below EI or intrinsic Fermi level, fine? So it may not be, this is also P type, this is also P type. So a student was asked to fabricate a MOS using the below semiconductor such that a following parameters it will have, okay? So now let's see. Let us fabricate the MOS structure. Let's say this is your metal, this is your oxide, this is your semiconductor, okay? So this is your P type. And it is mentioned that this is threshold voltage. It is Cox, means Cox is what? Cox is nothing but your Eox over Tox. So this is, let's say, your Tox. Okay. So assume there is no charge within the oxide. Okay. If the voltage across the fabricated capacitor is VTH, what is the magnitude of the depletion? Okay. So they are telling us that there will be some voltage. For the time being, let's call this G, this is B. Okay. Do you know why this is called G and B? Let's say this is VGB. We are not bothered about whether it is VTH or not. Okay. So do you know, right, why it is called VGA? This is called gate, right?
Yes, sir. This is gate and other is body.
This is gate terminal and this is body terminal. So if I apply some VGB, so how will the potential drop across the MOS transistor? Where can it drop? Okay, first thing, this is a region, this is
T,
your metallic region.
T.
Will in metal there will be any drop of potential?
No, sir.
There will not be any drop. Okay, so your V metal, let's say, is equal to V metal, let's say some drop will be there, it will be 0. And what is the next thing? There will be some drop in the oxide. Should there be any drop in the oxide?
Yes, sir.
So let's call
The
that.
whole VG will be dropped there.
No. Why will whole VGB will be dropped there? There is semiconductor also,
Uh,
right?
Sir, that is oxide. Now oxide will be uh, insulator. So entire potential will drop on the
Okay,
insulator.
okay. Let's go back to this diagram, right? So what was my total potential drop? This was my total potential drop, right? If this is your Vs, then this would be your Vs.
Yes, sir.
So our entire entire Vs dropping across this? No, right? Some of this Vs will be dropping inside semiconductor also. Do you agree? See, what happens is that as soon as you apply a positive voltage with respect to this, there will be some positive charges on the gate. Okay, what it will try to do? It will try to attract negative charges from the P type semiconductor, deep in P type semiconductor, towards this surface. Why can't the charge be present inside the insulator? Because there is no free charge inside the insulator, right? So how can this P type will be giving negative charges? What is the easiest way? The easiest way to give it is, you see, you have this acceptor. Suppose you have this boron atoms sitting, right? Somewhere here, somewhere here. So it will get ionized, and these boron atoms, these ionized boron atoms will try to get attracted at the surface. That part we call depletion. Okay. If you have gone through the lectures, you would have known that the boron atoms will get ionized and it will be giving some negative charges. These negative charges are what you were talking about. Okay. Here also the same thing is happening. As soon as you are giving positive charges, some negative thing is trying to get attracted. Okay. That is why this negative thing you only yourself told, right? That there will be depletion region near the p type. And why there will be depletion region? Because you need to get these fields terminated, right? If you have some positive charges at this place, you have to have some negative charges this place for to get the field terminated, because you are in a you are in a system where your voltage is applied like this. Okay, so there will be a particular kind of charges attracted towards the surface. That part we call depletion. The opposite charges, whatever is there in the gate, the opposite type of charges will get attracted toward the interface. Okay, now what happens if you keep increasing your VGB, right? This field will also start to increase. How? Because if your this Vs, if you increase the Vs, this line will also be, this line will be higher somewhere here. If your Vs is higher, then this drop will be also higher, and this will also get like this much stretched. So if your this voltage across the semiconductor, if we call it psi s, will also get increased, and your psi ox will also get increased. So for that, what will happen? The electric field or the slope of this curve will also get increased. As your electric field at this interface will get increased, more number of negative carriers will try to move toward the surface. After some times, the minority carriers will start in this depletion region, will start to move towards the surface and will create an inversion layer. Okay, so what we have basically, when we apply a positive voltage in the gate for a p-type substrate MOS structure, we will have two kind of negative charges to compensate those positive charges on the gate. One will be your depletion charges, another will be your minority carriers attracted towards interface. The interface we mean silicon dioxide silicon interface. Okay, so you see why the entire VGB will not be dropped across that oxide only. Do you get that? Partsarthi?
Yes, sir.
So you understood, right? Why the entire voltage will not be dropped across this? We did it step by step, right? If it is only metal insulator, then it would be dropping across this only, across the insulator. But then if you have an insulator and semiconductor, some portion will be, this portion will get dropped in the semiconductor also across that depletion region, right? Please tell me if you have any difficulty to
Yes, sir.
understand at this stage. So there will be a potential drop. Let's call it psi
Net
of,
was disconnected, so had
sorry.
I had joined
Okay, so what I was telling that
when the
the
charge will inverted and
no, this part you have understood, right? This part you were present, the insulator semiconductor part.
yes sir.
So you saw that, right? Entire Vs will not be dropped across this only, this oxide. It will be dropped in oxide as well as in semiconductor also, right?
Yes sir.
So here also the same mechanism will be happening. So the entire VGB will be dropped across your oxide and your semiconductor. Some portion in the oxide, some portion in the semiconductor. Okay. So now this is assuming the fact that your work function of metal and work function of semiconductors are same. But if those are not same, then a certain amount of potential will get dropped to balance that also. That we have seen in your metal semiconductor contacts. Similar kind of phenomena will be happening here also. So if you have gone through the lectures, so you will see that your VGB will be dropping across your metal semiconductor work function, oxide and your semiconductor. Around that depletion region, what will be forming inside the semiconductor just beneath the interface. Okay. So this is attributed to set a quantity called your flat band voltage. Okay. And I request to please go through the lectures because everything explaining here will not be possible for me. Otherwise, it will one question will take itself the entire class. Okay. So basically, what happens? Just let me briefly tell you. You have this kind of structure, right? This kind of MOS structure. Let's say earlier these are not joined. Okay. So you will have some E0. You will have some EFM. Fine. Let's take this metal work function is 3.87 volt. Okay. So this is, let's say, 3.87 electron volt, and the semiconductor work function, how much they have given. What is the semiconductor work function from this? Can you tell me? What is the semiconductor work function? What is phi fs or phi s? Anyone? This should be pretty straightforward, right? The semiconductor work function is nothing but the distance between vacuum level to its Fermi level. What is that? 4.5, and this is your zero point 0.3, right? Because this is also 0.5. So it will be what? 4 plus 0.5 plus 0.3. It will be 4.8 electron volt. So it will be 4.8 electron volt. This is E0, this is EF, S, and this is your EV, and this is here somewhere your EC. Okay. When not joined. Now if you join them, And to make a system, how will it look like? First thing, your Fermi level will be constant because there is no current flow. So this will be your EF. In this side you will have your E0. Somewhere here you will have your E0 for semiconductor. This is metal oxide, it will be semiconductor. Somewhere here you will have your EV, and somewhere here you will have your EC. So obviously the bands will start to bend. This will be your potential profile. Similarly, it will also start to bend. Okay. So this is your equilibrium condition. Now to make it flat band, what is flat band? Flat band means all the bands in the semiconductors are flat. To make it flat band, you need to push this thing upwards, or you need to apply some voltage which will get your EF. There will be, it will create a difference between your EF and EFS and EFM. So that way, when no oxide charges are present, if oxide charges are present, then there will be additional terms also. Okay. So this is called your flat band voltage. So whenever you apply some gate to body voltage, some portion of that voltage will also be consumed by this to balance this one. Okay. So your VGB can be written as VFB plus psi S plus psi ox. Okay. This is nothing but your phi ms plus psi S plus psi ox. Now this can be written as your gamma times psi S. What is your gamma? Here your Na is p-type substrate doping. Cox is Eox over Tox. The unit would be your farad per centimeter square or some area. Fine. So, and VTH or threshold voltage is equal to VGB, where your at the interface the substrate will be as much N type as it is P type in bulk. What does that mean? That means that if you draw the band diagram, let's say this is your EF and let's say this is your EI, this is EV, this is your EC, and this is somewhere here your E0. So you have a certain potential applied across your this. First thing that this will not remain same. So let me just remove this part. You assume it to be metal oxide semiconductor. So if we call this quantity phi f and this quantity also phi f, so you see that beyond this it is n type, right? Because your EF is over EI. So at the surface EF is, what did I write? That at the interface the substrate will be as much n type as it is p type in the bulk. What distance, this distance determines how much p type or n type my material is, right? You remember, right? N is Ni times exponential EI minus EF over KT, right? Minus of that, as your EI minus EF will be, or let me write it in this way, EF minus EI over KT. As this distance will be more will be my n-type material, and this distance I am calling it as phi f, q phi f. Okay. So what is the effective band bending? Effective band bending is nothing but 2q phi f. And what does this band bending translate to? This band bending translate to the potential drop, because we know, right, that if my energy band diagram is like that and then my potential will be like this. This is my phi profile. So the drop across semiconductor, which I am calling it as psi s, will be nothing but this drop divided by q. So what will be my psi s at threshold voltage condition? Psi s is equal to nothing but 2 phi f when VGB is equal to VTH. So I can replace here VTH equals to phi ms plus 2 phi f plus gamma root over 2 phi f. Fine. So what is the VTH given to me? VTH given is minus 0.16. And what is phi ms? Phi m was how much? 3.87 minus, this is my 4.8 plus, what was my phi f? Phi f given was 0.3 volt. So it will be 0.6 plus gamma root over 0.6. So it will be how much? 0.93 minus 0.16 is equal to 0.6 plus gamma root over 0.6. So this will be 0.77 minus 0.60 gamma root over 0.6. So this gamma quantity will be nothing but my 0.17 over 0.6. Fine. So we were asked to find out, depletion charge per unit area, right? So what will be my depletion charge? If this is my psi s We have seen that this will be my electric field profile. This is the interface. This will be my electric field profile. And from this electric field profile, what can we draw? We can draw the rho. What will be rho if my electric profile is like this in P type? So this will be my depletion width, and this will be my entire depletion. This will be my rho profile. So I want to find out this depletion charge, right? Fine. So how can we find out that? Your QD is nothing but your, how can you write that? You know your Cox, right? Now assume like this. This is your metal, this is your oxide, this is your semiconductor. You have some charge at this place. This is your oxide, TOX, and there is some positive charges at this plate. Okay. So if you do the analysis, you will find out that your Cox is nothing but your QD over psi ox. Okay. All the quantities are per unit area. So your QD would be nothing but your Cox times the potential drop across the oxide. And what is that? That is gamma root over psi s times your Cox, that is your 0.17 over root over 0.6 times root over 0.6 into what is your Cox? Cox, we have seen that it is Eox over Tox, epsilon ox over Tox. What is my epsilon ox? It would be your 3.9 times 8.854, or is it given already? Yeah, Cox is given 100 nanofarad over per centimeter square. So it will be your 100 into 10 to the power minus 9 farad per centimeter square, and this farad times coulomb will give you volt. Sorry, farad times volt will give you coulomb. This unit was volt, right? This is psi ox potential, the unit is volt. So this will get cancelled. So you will have 17 into 10 raised to minus 19 coulomb per centimeter square. Minus 9 coulomb per centimeter square. Okay. So the orders are not matching. So none of the answer option will be correct. So please tell me at this point. I know that I could not explain every concept in great detail, because that's what for you to read the lectures before coming to this kind of sessions. So given this discussion, you have any query, you can please ask.
Sir, gamma.
Gamma is nothing but your this quantity, right? So this formula I have written from here to here. This you please refer back to the lectures, okay?
So
Gamma,
lecture,
yeah,
in lecture this is not there.
gamma is not there.
No, sir.
I am not sure how come gamma is not there.
Sir, sir had written Vg is equal to
Okay.
VFB plus psi s plus TOX epsilon s by TOX.
Yes, so repeat once.
Vg is equal to FB
Yeah. Instead of Xiox, what he has written?
uh, TOX into epsilon s by TOX into ES.
TOX over in times epsilon x by
EOX into ES.
ES. What ES? Capital epsilon S
Uh,
or ES?
ES. Both are
Elect
there.
electric
Epsilon.
field.
Yes, sir. Electric field of the semiconductor.
Okay.
Of the.
Okay. Then go on.
Yes, that's it.
TOX over you are seeing, right? I am writing what is that? Is it what he has written? Instead of Xiox, you are
TOX.
TOX,
Technical.
okay, times
ES. ES.
ES
Epsilon is by epsilon OX.
epsilon OX, right?
Yes, sir.
Okay. So what is your ES and your epsilon S by your this is Cox, right?
Yes, sir.
Okay. So let's see whether these are the same thing or not. So ES you have, what is your ES? ES is this quantity,
Yes, sir.
right? So this is ES, let's say this is your W depth. So half into ES times W depth should be equal to your psi S, right?
Yes, sir. Yes, sir.
And ES times epsilon S you are telling, right?
Yes, sir.
Let me just check the dimensions once. Okay, this is cancelling, this is cancelling. This is volt per meter. Okay, you can do that. So if it is your psi S, then okay, let's do that also. Tox. So what is your ES? ES will be your nothing but Q. What is your ES? ES will be nothing but your Q times Na times by epsilon S times W depth. Fine. Do you
Yes, sir.
agree with that? This is nothing from Gauss law, right?
Yes, sir.
So if you agree with that, then this is Q Na times epsilon S. And what is your W depth? Under full depletion approximation, we know it is 2Es. 2Es, the potential over QNA, right?
Yes, sir.
This you know, right?
Yes, sir.
So if I just do the shorthand, what will do the cancellation? ES will be, so your QNA will be upstairs and your ES will be downstairs, right? Is this fine with you?
Yes, sir. Yes, sir.
Now, if I multiply epsilon S with ES, so 2QNA times psi S over epsilon S, so that will give me nothing but this quantity, epsilon S times 2 epsilon S times Q times Na times psi S. Fine.
Yes, sir. Yes, sir.
That is, now if I take Cox bottom end, epsilon S Es over Cox, it will give me what? 2 epsilon S Q Na times root over psi S over Cox. This term I am
Yes,
calling
sir.
gamma. Okay.
Yes. Yes, sir.
Is it clear now that these are the same
Yes, sir.
thing? I was not aware actually, okay, that this was not in the lecture. But you can see, remembering those formulas will may be very difficult for you, okay. So when you go for higher order degrees or higher order higher courses, you will find that this gamma comes very handy, okay. This is called actually your body factor. This we will discuss later also in today's session. So you can do it either way, okay. You can use this formula also. This will lead to you same thing. You just need to know the physics, okay. If you know your PN junction, because this formula is coming from your PN junction, right? Your
Yes,
built-in
sir.
potential will be there. Remember, plus minus
Yes, sir.
VR, the applied voltage. Here, the what is the built-in potential? Built-in potential nothing but is the band bending, right? The entire band bending was my built-in potential. Here it is nothing but my psi S. So this is nothing but the built-in potential in that sense. It is not called built-in potential, but you can call it built-in potential. So this formula, if you can remember, then everything is falls into place. Okay. So in the same manner you can do. Apart from that, do you have any problem on understanding?
No, sir.
So you go through it once, okay? Try to understand. So everything you know, okay? So far, whatever has been discussed, you know everything. So what is the basic difference you did not know earlier? This part, okay? This is what physics you have not been taught yet before MOS Cap. PN junction, metal semiconductor, everything you know, you can apply all those things, including this. So you will calculate, you can calculate the MOS cap electrostatics. Okay. So moving on to the next problem with reference to previous, what is the value of phi ms? Phi ms we have calculated, right? Did we calculate phi ms? What do you say? Have we calculated phi ms? Parth Sarthi?
Sir, didn't remember.
Yeah, we had to calculate it, right? That is what I was checking. I know that I have calculated because VAB you need to calculate, right? So phi ms you must have calculated. So please try to follow the process carefully, okay? So phi ms you have calculated out to be, this is minus 0.93, right? So yeah, phi ms was calculated. Phi m was 3.87 and phi s was how much? 4 plus zero point 0.5 plus zero point 0.3. Okay. So let's move on to the next problem. Okay. Okay. So Let me draw a graph for you and you tell me that do you know this thing or not? Let it be Q. Has this has this plot been discussed in the lectures? This is under your, let's say, region 2, region 2, and let's just draw the same thing again. There will be very high number of inversion. This is the case for region 3. And what about region 1? Region 1 would be something like this. Let's say there will be negative charges here, so there will be positive charges here. Let's say this is grounded. This is Vg less than Vth. This is Vg greater than Vth. This is Vg less than Vfb. Okay. So this is P type. So this is, let's say, region 1. This is region 3. So this thing called accumulation, this thing called inversion or more strong inversion, this is called weak inversion or depletion. So was this discussed in the class?
Not exactly. He make the graph with capacitance between capacitance C and Vg.
Q he didn't tell. I think he has also told Q, right? If this is your Q, then what will be your capacitance? What is your capacitance basically? C is nothing but dq by dvg.
Yes, sir.
So if you mark these 2 points, so what will you find? You will find a straight line here.
Yes, sir.
You will find you will find some kind of this plot here, and again you will find this, right? This is
Yes, sir.
this
Yes, sir.
plot, you know. This is nothing but the
Yes, sir.
derivative of the above plot.
Yes,
Okay.
sir.
So
This graph has he discussed.
so you see, right, that how this is coming. You know that why this is coming or how this is coming. You see, this is linear, right?
Yes, sir.
This is linear, and this is some kind of quadratic behavior. Okay. So what happens when your Vg is much greater than Vt? When your Vg is or Vg is greater than Vth or threshold voltage, what happens? That these charges are called your inversion charges, right? Qi, and these charges let us call Qd or depletion charges. Okay. So what happens is that as you increase Vg, your psi s also increases. What is psi s? Psi s is this drop, and how this increases I have shown here, that as you increase your Vs to this value, this 4 point will also push up to this point. So your psi s will also get increases. By the way, psi s is called surface potential. Okay, what does that mean is that the potential will drop like this, right? If this is your metal, this is your oxide, and this is your semiconductor, and this is, let's say your phi ms is 0, okay, or your VFB is 0 for the time being. So this will be your VGB, this is your VG, this is your VB. Okay, do you get that?
Yes, sir.
If this is VGB, then if at this point, not entire, this is your psi ox, okay, some portion of the gate voltage is dropping across this oxide, and then the remaining portion is dropping in the semiconductor within this region, because in this region no change in potential, right? So this psi s is called surface potential. That means how much my surface is above the bulk potential, or VB. Psi s is nothing but how high or low surface. What do you mean by surface or interface? This thing, okay, this interface, this is what we mean by surface or interface. How high or low the surface potential is with respect to body or bulk. Okay, that is called your surface potential or psi s. And why does psi s happen? Because there is a certain amount of region where I have the depletion charges. So across this my psi s will be present. And why do I say that? I say that because you remember, if there is some non-zero row, that will be creating this non-zero kind of row, will be creating some electric field, right? And this electric field will be creating some potential. If this is say positive, then how will my electric field be looking like? Electric field will be one integration, right? So it will be, let's say, my electric field E will be like this, and then my phi or potential will be something like this, quadratic. This is, let's say, linear, so it will be quadratic. So you see, this potential drop is due to what? Due to the presence of non-zero charges, right? So wherever there will be non-zero charges, there will be a potential drop in the semiconductor. So as there is a depletion region, So across it there will be a potential drop, and that potential drop we are calling as a surface potential. So as your Vg increases, psi s increases, and psi s tend to saturate to 2 phi f. Okay, as my Vg increases, after some time this boundary will not further extend and it will get fixed somewhere here. So then if I keep increasing my Vg, these positive charges will keep increasing. So I need to add some more negative charges to compensate the field lines. So from where those charges are coming? These charges are the minority carriers generating from this depletion region. This is called the inversion charge, this charge Qi. So if you see, your Qi would be nothing but your Cox times Vg minus Vth. Okay. So if you see this line is that equation only. If this is equation A, this line is equation A only. Okay. There will be Qd, but Qd will be very less compared to Qi. Similarly, here will be a quadratic drop. This I am coming to. And this will be accumulation. Accumulation means what? If I apply some negative charges, I will have holes abundant, right? Abundant holes are there. So all holes will be, some of the holes from this substrate will be getting attracted to the surface. So this will be just like a parallel plate capacitor. So this region, it will also be proportional to, or Q would be proportional to, let's say this is your QA will be equal to your Cox times your Vg minus VAB, something like that. So you see, if you do dqa over dvg, you will have Cox as a slope, constant slope. So that's how you are getting this here Cox, this value. Okay, and in this region, this Qd will dominate. This charge Qd will dominate. So you need to find out how Qd relates to Vg. How will it relate to Vg? If your Vg equals to VAB plus psi s plus psi ox, right? So what will be your Vg? Vg will be is nothing but VAB plus, what is your psi s and Qd relation? This we have done earlier, right? Somewhere here. This is your, this was your Qd, right? Your Qd is nothing but Qna into W depth, right? So Qna times, what is your W depth? Root over E epsilon s times psi s over Qna, that is your Qna 2 epsilon s into psi s. This quantity Qd is equals to Cox times root over 2q epsilon s Na over Cox times root over psi s. That means Qd is nothing but your Cox times root over psi s into gamma. So what is your psi s? Psi s is nothing but Qd square by Cox square times gamma square. So if you just put it here, Qd square by Cox square into gamma square, and Ψox, you know that it is QD plus QI over Cox. You can see that Vg is a QD square relation, quadratic relation. If you plot it, it will, if you plot QD as a function of Vg, it will show like this, okay? This kind of quadratic nature. And when you do the derivative, when you take the derivative of that, you will find this kind of nature, and then these lines are just constant line. This will be Cox and Cox. This is how the CV curve of the MOS cap is coming, okay? So now in the question it is mentioned that at Vg equals to 2 volt, it is under strong inversion. So this part we call it strong inversion, means which region we are in? Region 3. So what is my region 3? This is my region 3. So I am in this part, okay? According to question, I am in this part. So let's say this value somewhere here we are in 2 volt, and 2 volt inversion charge density is 2.2 microcoulomb per centimeter square. We are talking about the modulus of the charge. Obviously for a p-type substrate the inversion charge will be negative, so it will be minus 2.2, right? So we are in the bottom half of the quadrant, so the sign convention is correct, okay? And they are telling us that what will be the inversion charge density at Vg equal to 4 volt. That means what will be this in 4 volts? It will keep continuously growing. So they want us to find out what is this point's value. So it is pretty simple, right? It is just a straight line. So Qi at Vg equals to 4 volt will be how much? This entire height, this entire stuff, this I can break into this much I know. What is that? 2.2 plus I need to find out what? This height, right? This height remaining. This height I need to know. And that I can easily find out from this. How can we find out? We know that Cox is the slope. So this is, let's say, Qi2. So your Qi2 would be nothing but Cox times Vg2 minus Vg1. Cox is given as 1.7 microfarad per centimeter square. Microfarad per centimeter square times, let me take this way, times your 4 minus 2 volts. So farad into volt will be my coulomb. So 2, it will be 3.4 microcoulomb per centimeter square. This distance, this height, and we already know this height, that is 2.2. So it will be 3.4 added. So how much it will be? Will it be? It will be 5.6 microcoulomb per centimeter square, right? So 5.6 per 5.6 microcoulomb per centimeter square. This will be your right answer. So what is the crux of the problem? The crux of the problem is that you need to understand that in strong inversion, the slope of the QV characteristics does not change. It is Cox because it is constant here, right? It is constant. So if I am at 2 volt and it is already the value is given and I know Cox, so I can easily find out what will be at the deep in strong inversion, right? In much higher strong inversion, or Vg equal to 4 volt per se. So this can be easily calculated. So did you get that, Partsarthi?
Yes, sir.
So what is the crux of the problem according to you? What did you understand from this problem?
The same thing that you mentioned, that Cox will be constant in
Okay.
inversion region.
Cox will be constant in strong inversion region or inversion. In conventional, it is called inversion, but you try to call it strong inversion. Okay.
Yes, sir.
So in strong inversion region, it will be constant Cox. So Q will be linear, right?
Yes, sir.
So if Q is linear, so I can easily find out from the line. We can find out from the straight line equation or some graphical method. Just I have shown. Okay. So
Yes, sir.
try to understand and remember this plot. Okay, this is very important. And also, if you take one consequence, you can see what is this point, by the way.
This is metal
This
side.
no, this point is VFB voltage, right? I am not
Yes,
talking
sir.
about metal side. There is nothing to do with
Yes, sir.
metal side. This is a QV plot,
VAB.
right?
Yes,
So
sir.
this is VFB. So you see at VFB, what will be the charges in the semiconductor? Suppose I am applying VFB, okay? Depending upon some plus or minus, whatever charges it will be with respect to bulk. So at VFB, what is the charge at semiconductor? QS equals to QI plus QD. What will be that? What will be the depletion charge and what will be the inversion charge? From this plot, what do you see? At V equal to VFB, what is the Q?
Sir, zero. No
Q is
charge.
0, right? No charge.
Yes, sir.
So you understand that, and again I have told you what is my VFB condition, right? At VFB, VFB means flat band, right?
Yes, sir.
All the bands will be flat. And also I have told you that to accommodate some charges, you need to have some band bending.
Yes, sir.
So if your bands are flat, by default you can assume that there is no charge in the semiconductor, right?
Yes, sir.
So what about the gate charges? How will this get compensated? This has to be compensated, right?
Yes, sir.
So your VGB is equal to VFB plus psi ox plus psi s.
Yes, sir.
So if your VGB is something at VFB plus psi ox plus psi s, so your psi ox will be plus psi s will be equal to 0. Okay. This will lead to, if you do mathematically, this will lead to your QS or QI plus QD will be 0. So remember that at flat band, there will be no charge in the semiconductors. Okay. Neither positive charges nor negative charges. So if this is VFB and this is, let's say, VG, at this place what region will I have? I will have accumulation, right? And beyond that I will start to get depletion,
Depletion.
then weak inversion, then after VTH I will get strong inversion. Okay, and what about your if I same thing, if I do with psi s at VFB translates to 0, okay, and VTH translates to 2 phi f. So this is accumulation, this is depletion, weak inversion, this is your strong inversion. Okay, so psi s is negative in accumulation. So by the way, what did you feel by after this much discussion, that which voltage is the most important in analyzing this kind of devices? What is your feeling? Just get to know. Yes, you see that if you know this quantity psi s, right? So you can cover up almost every other aspect of the device, because if you know psi s, you know this distance w depth. As soon as you know this distance, you know this entire charge, because you know the doping prior hand, right? This you know, so you need to know w depth. So as soon as you know w depth, that is depending upon your psi s. Similarly, if you see me writing the equations, that your this psi ox we have seen, right? It can be written as gamma root over psi s. So your psi s is most important potential in the MOS structure. Okay, if you have the comfort to deal with psi s, or if you get comfortable with dealing in psi s, then you can understand and analyze each and everything. Okay, so this is the most important potential you should be aware of when analyzing the MOS structures. Okay, so let's move on to the next problem. So in this problem I will assume that you know about what is body effect. So your VGB or VG is nothing but your what? VFB plus psi s plus gamma root over psi s. Okay, so your VTH is what? VFB plus 2 phi f plus gamma root over 2 phi f. Let's call this VTH 0. Okay, now if I apply, suppose I have, so far I was having this kind of structure, right? This is my oxide, metal oxide semiconductor. This is B, this is G, and now let's say I have some contact here. This is P type, this is some N plus contact. there will be depletion charges, and there will be inversion charges. Okay. So let's say I have this kind of contact which I am calling at B. Sorry, this I am calling at source, and I am applying some potential here. Okay. So your new VTH would be your VTH 0 plus your gamma root over 2 phi f plus VSB minus root over 2 phi f. This I am assuming you know. Okay. And if you do not know, please go back to the lectures, because I need to cover almost 4-5 problems in 15 minutes. So this much, this is from the point where the professor has discussed body effect. Okay. So now if you do dVTH over d mod VBS, what will you find? You will find 1 over, this is constant, this is constant, this is constant, this is constant. So what will you do? Will you find? You'll find that gamma will remain that, and 2 root over 2 phi f plus mod VSB. Okay. So what about your delta VTH over delta VBS? This is given as 50 millivolt per volt. Gamma is what? Gamma, let's say, let us calculate gamma only. 2, and it is given that VBS plus 2 phi B. VBS is much greater than 2 phi B. Generally your phi B is of the order 0.3 or 0.4. Okay. So and 2 volt is VBS given. So I will take 2 plus some 2 phi F. So which we will consider as 2 root 2, because this is very small. So gamma will be equal to 0.05 times 2 root 2. Okay. So what is your gamma? Root over 2q epsilon s times Na over Cox 2 root 2 into 0.05. So what will be your Na? Na will be Cox square 2 root 2 into 0.05 square over 2 into q into epsilon s. That will be, what is Cox? Cox is Eox square over Tox square times 2 root 2 0.05 whole square over 2 into q into epsilon s. So if you do that, and everything is calculated in centimeter cube. Okay. So Eox will be what? E is given as E4 and 12 it is given. So Eox will be 4 times 8.85 into 10 raised to minus 14. And what is your Tox? Tox is given at 10 nanometer. That means 10 raised to 10 into 10 raised to minus 7 centimeter square times 2 root 2 into 0.05 whole square over 2 into 1.6 into 10 raised to minus 19 into, what is your epsilon s? Epsilon s would be 12 into 8.85 into 10 raised to minus 14. Okay. So if you compute it, it will come out to be your 7.37 times 10 raised to 15 centimeter cube. Okay. So did you able to follow the flow of the problem? So
Yes, sir.
you need to find out this. Okay. So that's where the gamma is becoming important. Okay. If you know the formula with this quantity, then it will be easier for you to calculate gamma, and gamma you can easily understand or remember whatever feel way you feel comfortable. 1-2 times you need to do it yourself, and then you will find out that yes, this is the same quantity. So this is your gamma, right? Once you get to understand what gamma does, then you will be able to understand that how my this formula it will be getting imprinted in your mind. Okay. So another thing, what is the significance of your gamma is that you see gamma is the quantity, gamma is the factor which is governing VTH or threshold voltage with respect to body bias or VSB. Why do we call it body bias? Because generally we take source as a reference potential, okay, for a 3-terminal or 4-terminal devices. Though body is also taken as reference potential, reference node most of the times, okay, but source is also does the same thing. But conventionally or traditionally, source was to be taken. So every formula you will find in old books that it writes VGS rather than VGB, okay. So that's why your VBS becomes your body potential, or how much potential the body has with respect to source or the reference potential. Okay. So that's why gamma is called body factor or body effect coefficient. Okay. So moving on to the next problem. It is mentioned that an ideal MOS capacitor has boron doping concentration of this with a gate voltage is applied, depletion region width is this, formed surface potential is this, given that this relative. Okay. So can you tell me what is the region of operation from the statement from this line?
Sir, it is strongly inversion because plus 2 volts.
No, the from that value can be changed, okay, depending upon your metal semiconductor work function, that value can be changed. Generally
Sir,
it is in strong
positive.
inversion, but can you tell me that no, you just tell me in which regions, possible regions are what? If you have a depletion region formed, right, it will be either in this or this, okay. That means it is more than flat band, right? That much we are sure, but
Yes.
whether it is in strong inversion or not, that we are not sure, because at strong inversion my depletion region will not increase, okay, but no information has been given in that regard, okay. So now let's take this MOSFET, sorry, MOSCAP, and it is mentioned that upon some potential given, some depletion layer has been formed, and this width is how much? 0.5 micrometer. Okay. So can we draw the charge profile? Row profile we can draw, right? So how will the row profile look like? Row profile will be somewhat like this. Is it okay with you?
Yes, sir.
And what about this? Now this will be interesting. What about this? If I have to draw the row profile in metal also, what is the charge profile in metal? I have discussed it many times, right?
Yes, sir.
So what is the charge profile in metal?
Sir, same plus invert that. Same
Plus
amount
invert
will be
that same
inverted.
amount, but how will I draw it? Should I draw like this? Should I draw like this? Huh? Should I draw like this?
I don't know, sir.
No, no, think it logically, right? What does this mean? This means that charges are over a region, right?
Yes, sir.
But
Sir,
in metal,
it will be like a spike, impulse
exactly,
function like something.
exactly. Now you are getting it, right? I am very happy that you are able to answer that. It will be a impulse function, right? It will be sheet charge. At this point only, at this interface only, there will be a sheet charge, right? This we have discussed in metal semiconductor junctions, remember?
Yes, sir.
So yeah, absolutely. I am very happy that you have started to visualize that how the charges are there in the metal, because metal is a equipotential surface. All charges will be at the end or the surface, right? So it will be at that position where there will be the spike or the impulse function or the sheet charge. Okay. So now quickly tell me that how will my electric field profile look like?
In metal side, impulse will become
No, no, no,
step
no, no, no,
function.
no, 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 no.
Huh?
Start with semiconductor side. It will be easier for you.
It
First
will
thing
be
was
linear.
what? It will be linear, right?
Linear.
And
Yes, sir.
linear, I can draw it like this and like this also, because the slope should be negative, right? This negative is
Yes, sir.
translating to this negative side, okay? So this critical things
Yes.
you try to visualize, okay? So I will be drawing this electric field like this. And what will be happening at the interface? There will be a jump, right?
Yes, sir.
Why there will be a jump?
Because discontinuity.
Discontinuity, why? Because these are two different
Uh,
materials, right?
yes, sir. Epsilon are not same.
Yes. So my D's are same, but epsilons are not same. That leads to my E's are not same. Okay. Remember this point. This is the most important thing, or only thing. If you want to remember the only thing from this session, remember this thing. Okay. So there will be a discontinuity, and then there will be a like this. And what will be the this one? What will be the impulse? In metal, electric field is zero, right? So
Yes,
you
sir.
see, now you see the beauty that physically you know that in metal there will be no electric field. So you have just drawn a zero line, and in semiconductor, in insulator, you have this. Now you need to join this. You are joining this like from intuition. Now see from mathematics that when you do the derivative, if there is a step function like nature, there will be impulse. If you do the derivative d dx of this plot to this plot, so you will see step like impulse, right?
Yes, sir.
So you see the mathematics is also validating the physical sense. So, and what will, and how will the this one will look like, and how will my potential will look like? Potential
It will be,
quadratic,
yes, sir, and then linear.
then linear, then in metal is what?
That will be constant.
Why? From physics,
Uh,
metal is an equipotential surface, right?
yes, sir.
So this will be the nature. So now quickly tell me if this is my Vg, right? Assuming that phi ms is equal to 0. This is my Vg. So what is this? Psi ox drop in
Yes,
this
sir.
region. And what is this? Psi s.
Uh, yes, sir.
So you are understanding, right? How am I telling that it is drop in this region? Drop means what? From this point to this point, if I move along right hand side direction, my potential is dropping from this point to this point. So that is why I am telling that in oxide my potential drop is this. Okay, so now if this is the case, we have been given that the ideal MOS capacitor has a boron doping concentration this silicon this peak electric field. Okay, what is the peak electric field in the oxide? This is the peak electric field EOX, right?
Yes, sir.
And let's call it ES at this point. So what is EOX is equal to 3 times ES. How do you know that? Because EOX times EOX is equal to epsilon SI times epsilon S. So epsilon ox is equal to epsilon SI over epsilon ox times ES. So it is 3 times ES because it is 12 and 4. You understand this, right?
Yes, sir. Yes,
Okay.
sir.
So if this is the case, then EOX, ES you know. What will be your ES? Okay, let us calculate ES. Okay. So what do we have? We have depletion width of 0.5 micrometer. Okay. So this distance we know it is 0.5 into 10 to the power minus 4 centimeter. Okay. And what do we know? We know that my psi s is, this value is what? 0.2, right? Psi s is 0.2, 0.2. So from this plot, can I write that if I take this triangle, okay? If I take this triangle, can I write that my psi s is equal to area under this curve,
Yes, sir.
W depth times ES? So my ES would be what? 2 psi s over W depth. So what is my 2 psi s is 0.2 and what is W depth is 0.5. 5 times 10 to the
5.
power minus 4, and this will be in volt per centimeter, right? So what will be my EOX? EOX will be 3 times of that. So 3 into 2 into 0.2 into 10 raised to 4 over 0.5 volt per centimeter. That is 3 to 2. It will be 12 over 5 times 10 raised to 4 volt per centimeter. That will be how much? 2.4 into 10 raised to 4 volt per centimeter. So this will be correct. It is in micrometer they are asking. So we know that 1 centimeter is 10 raised to 4 micrometer. So it will be 4 micrometer. So if you can visualize rho, you can visualize E, you can visualize phi also. Okay, potential also. So you see everything is revolving around the same principle we have discussed earlier. Additionally what has been added? This thing has been added today. Apart from that, everything you know. If you know rho, you can calculate electric field, you can calculate potential also. Okay, so this was pretty easy. Can you tell me what is the CV characteristics? I will conclude with this. Or let us do it in the next class. I think we are well above time. Okay, so that is all about today. If you have any question, you can ask.
No, sir. Thank you.
Okay, try to read the things carefully. Okay, concepts, and try to solve
Yes,
the
sir.
assignments. Okay, so let's close the session.